Welcome to Study Loop.
Hi everyone. So we're trying to solve exercise 10.1 here, and this exercise asks us to calculate the torque, including the magnitude and the direction, about pivot point O. So this is this fat black point that I am drawing out here. And in each case, we have a force that has a magnitude of 10 newtons. So that is indicated by this red arrow. And we have a rod that's 4 meters. So that's just these black lines. So we can see that it's same rod, same force, same pivot, but it's the force is acting on different ways, different directions, and different point of contact. So how do we find the torque? I think let's first write down the formula for torque so we have an idea of how to get started. We have so the book gives a variety of formulations for the torque. One is F times L, in which F is a magnitude and L is a lever arm. But we'll find that the more useful formula is F tangential. I'm able to type subscripts here, so just use Ft to indicate F tangential, times R, where R is the distance between the point of contact to the pivot point. And we have this way because usually R is much easier to find than the lever arm. And Ft, we can find it just by decomposing the force into the tangential part and the radial part. But let's first get started and see how it works out. So for the very first case, that is this one, we have a force that is 90 degree. It's acting completely tangentially, that means. So in this case, the force itself, the entire 10 Newton is tangential force. So we do not need to bother to decompose the force because we already know everything's going to be tangential. So that's great in that we can just plug everything into the form. I'll just give us a little bit more space over here. So that's great in that we do not need to decompose the force, and we can just write tau equals Ft is just F, so it's 10 Newton times R. R is the distance from the pivot point to the point of contact this red arrow is pointing. That's the entire length of the rod, which is 4 meters, and that gives us 40 Newton per meter. Don't forget the unit. So this will be the torque, the magnitude of torque for the first case. And let's check out the second case. Here things are a little bit different in that we have this angle that is not 90 degree anymore. This is, the question says 120 degree. So we do have to decompose this force now because it's not completely tangential. And using the vector addition that we should be very familiar with by this point, we can decompose it into two components. One is tangential to this rod, or perpendicular to this rod, and one is the radial component, which is along the rod. And we can see this component, this one is the tangential component. This is the force, the part of the force that causes the rod to rotate. After all, torque is what causes something to rotate. And this is a component we're looking for. And what about this? What about this one along the rod? It doesn't really do anything. It is used to compress the rod, but it does not cause it to rotate. So that's the reason we do not need this part. So let's first try to calculate the tangential part. The tangential part here, we have, this is equal to, we need a little geometry here. This is 120. That means this is 60. So if this is 60, we have F tangential equals F. So tau F 10 Newton times sine of 60 degree. And what sine of 60 degree? If we put it into the calculator, we know it's square root 3 over 2, or it's around 0.3 0.86. So plugging that, we know that F tangential is around 8.6 Newton. And from that, we can calculate the torque. Torque equals F tangential. And again, what is R? R is the distance from the point this red arrow is pointing at to the pivot point, which is again 4 meters. So times R equals 8.6 Newton times 4 meters. So that gives us a total of around 34.6. Oh, sorry. So that is Newton per meter, again units. This is magnitude of torque for the second case. And the third case is actually rather similar, in that we can use the same kind of procedure to solve it. In this case, we have 30 degree over here. And we do the same decomposition. You can see in this, now we have a radial component that is used to extend the rod, but the tangential component is again sine 30 degree. So now we have Ft equals F and sine 30 degree. Sine 30 degree, again, if you put it into the calculator or if you remember it, it's just 0.5. So this is 5 Newton. And then we have equals Ft times R equals 5 Newton times 4 meter, which is 20 Newton meter. Okay, so this is what is happening for the first 3 cases. Let's move on to the next 3. For the first one, which is the one in the lower left corner, we see things now get a little bit different. Now you have a different point of contact. So this point of contact it's 2 meters towards the end of the rod. Since we know that the whole rod is 4 meters, we know this part is 2 meters as well. So this part. This is our we're looking for, from the point of contact to the rod, to the pivot of the rod. So that is 2 meters. So this, we do the same force decomposition, except that now we have R equals 2 meters instead of 4 meters. But if we follow the same procedure, now we have this is 60. And we again decompose the force. And we have the tangential component is F times sine 60 degree. So we've already calculated this. We know it's 8.6 Newton. And what changes is now we are doing it. When we do the second part, we calculate the torque, we are multiplying it by 2 meters instead of 4 meters. Because, and that gives us 17.2 Newton meter. Okay, what about this case? We can start to decompose the force, but let's first inspect this case a little bit. We have our point of contact right here. So the force is acting right on the pivot. So what is the lever arm? What is the distance between the point of contact and the pivot? 0, because we are acting right on it. So no matter what is the force, effective force, we can see when we do tau equals FL. FL or FT times R, we will see that R is 0. So no matter what the force is, we will end up with a torque of 0. So we don't even need to calculate it out. We can just tell it's 0. And that's the same for the last case. In this case, we are acting on this point, but the entire force is radial to the rod. So in this case, we have F tangential equals 0, because there's no tangential component of this force, and that again gives us power equals 0. And now we're done with calculating the magnitude of the torque. We have non-zero magnitude for 4 of these cases, but we have 0 torque for the next 2 cases, for the last 2 cases. So in the last 2 cases, no matter how hard you push, the rod is not gonna rotate. And if you just try to visualize pushing a rod on a fixed pivot or pushing a rod along the direction of it, it's to get some intuition of it, try to imagine doing that. And hopefully you'll reach the conclusion that it shouldn't be moving. So, but we're not done yet. In that we also need to find the direction of the torque. So how to find the direction of the torque? We have this thing called the right-hand rule, which is introduced by the book. So what it's saying is that for every torque, say we have the rod right here, and imagine we have a force anywhere. Say we have a force like this. What you should be doing is you should try to align your right. You should try to reach out your right hand and point the fingers of your right hand in the direction of R. So we have the R in this direction. So try to have your right hand and point your 4 fingers, not just your 4 fingers in this direction. Now try to curve them in the direction of F. So this is more like, this is a very 3D drawing, that if you look down and you try to point your, this is your thumb, imagine it's popping out of the paper, you should have your right hand curved in this direction. And this is your palm, this is your arm. These are your 4 fingers. This is just like a top view of your right hand. You should be aligning your right hand so that your so that your arm is aligned in this direction, but your fingers are pointed in the upward direction of the screen. And then you should have the thumb facing yourself right now. So that will be true for any force that's acting up. If you just try to curve your finger a little bit, you'll see that for any force that's acting up, you will have a thumb that's pointed towards you. And that is how you should be calculating the torque. The direction of the torque is you align your fingers along the R, and then you curl it in the direction of the F. And then your thumb will be pointing in the direction of the torque. So you see, for any force acting up, you have a thumb pointing towards you. So the torque will be pointing out of the page or out of the screen. And that will be applied for both 3 cases in the first row. If you try it out with your hand, and you'll see that the torque will be pointing out of the page. Or sometimes we denote this as having a circle and a dot. So that indicates going out of the page. And what about this case? These are just 0, so the last 2 are just 0, so we don't care about them. But this one is when you have your arm, again, it's still a right hand. You have a right hand, and this is a right hand, and you try to align the 4 fingers along the direction of this rod. So again, the pivot on the left, so it has to be, the 4 finger has to be reaching right. And then you try to curve them in the direction of the force. This time, this force is going down. So try to curve your fingers. So you have this. Then your thumb should be facing into the screen. It should be facing the same. It's the same direction that it's the screen. So this is into the page. And sometimes we denote that as have a circle with a little cross. Meaning something's going away from you. You can think of it as an arrow that's going away from you, and you are seeing its tails. So that is the direction for torque for this case. So torque points into the page. So that is all 6 cases that we're trying to solve. We have the magnitude and we have the direction. We have the 2 direction, and then we have 0. And that is it.